Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Design and Application of Intumescent with Protective Coatings. My name is Amanda and I'll be your host for today. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's long-standing industry partner, Dulux Protective Coatings. Dulux is a manufacturer and marketer of products that protect, maintain and enhance the spaces and places in which we live and work. From household rooms, transformed by the latest designer colours, to the industrial coatings that protect landmark infrastructures, such as bridges and the construction solutions that reinforce them. Dulux products are at work. Their brands have been woven into the fabric of the communities where they operate, helping consumers to live better and more comfortable lives. Today, we will hear from 3 speakers, followed by a live audience Q&A. And I encourage you to send through questions via the chat box in YouTube. I'd now like to welcome our first speaker today, Dr. Jonathan Barnett. Jonathan is an internationally acclaimed technical expert in fire safety engineering with over 42 years' experience in his field. Previously a professor at WPI in the US, Jonathan has researched topics such as computer modelling of fire, structural fire protection, combustible cladding, and the development of new fire test standards. Jonathan has done projects throughout the world, including the US, Europe, New Zealand, and Australia. Jonathan is a chartered professional engineer who has designed numerous commercial, residential, and special purpose buildings. He is a leader in building defect rectification strategies. As a forensic specialist, Jonathan has worked on numerous projects, both large and small, including the analysis of the events of 9/11. As part of the ASCE FEMA team, he testified before Congress on the events that led to the collapse of the buildings at New York's World Trade Center, now over 10 years ago. Today, Jonathan is the Managing Director of Basic Expert, a specialist forensic engineering and fire engineering firm, focusing on helping people with non-compliant buildings deal with dangerous cladding, inappropriate essential safety measures, fire, alarm and detection systems, fire-rated doors and the like, and helping them with building rectifications from design to permits to construction and through legal quagmire of litigation. Please welcome Dr. Jonathan Barnett.
Hello, my name is Jonathan Barnett. We're going to talk about the design and application of intumescent coatings and in general about fire resistance levels and fire protection. I'm the Managing Director of Basic Expert, a small engineering firm based in Melbourne, although we do work throughout the country and internationally. Today's talk is, as I said, going to talk about fire protection, fire safety, structural fire protection. We're going to talk about the real world. We're going to talk about the building codes deemed to satisfy world, which is not the real world. We're going to talk about what happens when there's something new in the real world and the code hasn't caught up with it yet. So we're going to start with some ancient history. And I guess we can't get much more ancient than Rome in the year 27. So in the year 27, there was a brand new Colosseum. There were 50,000 people in the stands and the Colosseum collapsed. 20,000 people were killed. Pretty horrific. What did the Romans do? They wrote a building code to deal with structural collapse. It's curious, of course, when we look at this particular stadium collapse, that the 50,000 capacity is the same as the new Adelaide Stadium. Imagine if that collapsed and 20,000 people died. Well, in the year 64, there was a fire. Rome was not having good luck during that century. And that fire, as you may recall, this is the one where Nero took charge and watched the fire. And he took charge and he put together some committees. And the committees wrote an addendum to their building code. So remember, they had that building code from the structural collapse, and they wrote an addendum to manage fire. And this is the first modern building code, because modern codes look at, of course, fire and structures. Those are the two most important things. There are other amenities and, of course, disability access, energy, and the like that we have in our modern code. But the bulk of our modern code is structural behavior and fire safety. And it's based very much on what was done by the Romans. So this is the modern era, this is where we're at, and it's where we are at throughout the world. How did we get here? Well, we had other fires. You can recall, of course, the Great Fire of London in 1666. What did the British do after that fire? They wrote a new building code, and it looked at structural behavior and fire safety. Basically the same things that were in the Roman code, but modernized to the year 1666. Of course, we were continuing to have fire problems, and we had great fires. We were busy burning our cities down in this era. So in Chicago, thousands of buildings and lives were lost in the Great Fire of 1871. In Sydney, we had the Great Fire of 1890. So this isn't just a Northern Hemisphere problem, but it's something that's occurred throughout the world. The 19th century was the century of great fires. Well, why did these fires occur? They occurred because of lack of access for the fire brigade. They occurred because of narrow roads. They occurred because of combustible cladding. And they occurred because of structural failures, structural collapse. And they occurred because of the lack of fire resistance that prevented fires from going from one building to the next. So this traditional approach, these traditional codes, are the bases for our deemed to satisfy provisions of our Building Code of Australia, of the modern code. The approach for fire resistance in the DTS provisions is globally accepted by virtually all model codes throughout the world. So we have a lot of commonality in our building regulations. What's a surprise to many is that the structural fire resistance is actually based on work done in America in the 1920s. So this work was done by a man named Ingberg at the National Bureau of Standards, and it became the basis for the British Code, the European codes, of course, the Australian Building Code as well. So this work in the 1920s turned out to be expensive. You had to do large-scale testing, and in fact, the biggest problem we have with it is that there's an unknown level of safety. So in the 20s, a series of tests were done. Ingberg put all the results together, and based on those results, developed the concept of fire resistance. Now, actually, some work had been done by Wolfson in around 1910, and a little bit of work done in the UK in the late 1890s. On the other hand, the basic approach was what was done by Ingberg. Now, this traditional approach ended up being codified in a series of standards. So AS 1530 Part 4, BS 476, ASTM E119, the American version, ISO 834, the international version. This is all a test standard that ties back to the 1920s work by Ingberg. Basically, you take a structural element, a frame or a barrier, and you put it in a furnace, and based on certain test criteria, you accept or you don't accept the results, and you get an hourly rating of how long that element survived in a furnace fire. Now, this fire resistance test was easy to administer. It obviously has a historical basis going back to the 20s, 100 years ago, funnily enough, and a database of materials and construction techniques that have been developed over the years, both in Australia and, of course, worldwide. And it is universally accepted. Now, this furnace is a standard size furnace, and the exposure, or how hot is it, is a function of temperature. Temperature changes, you change the amount of fuel you're using in the furnace, whether it's a gas or oil-based furnace, and the temperature changes as a function of time. And so the table you see on the right is a table of the standard time temperature curve that becomes the basis for structural fire resistance. The outcome of these tests is a fire resistance level, or a rating. The rating is in minutes, rounded down to the nearest 30. So you look and see, you put your element in the furnace, and you look to see when it fails an acceptance criteria, and you look at the time that took. You round down to the nearest 30 minutes, and that gives you the fire resistance level of the element you're testing. Now, in Australia, we look at three components. We look at structural adequacy, we look at integrity, and we look at insulation. The furnace on the right, by the way, is a New Zealand furnace, and the front is off. There's no specimen, it's just what the furnace looks like on the inside. Anyway, structural adequacy. This is where the element being tested fails to support a load. And the load is either the standard load that's applied to the elements, so a column or a beam or a floor will have some sort of a load, or it could be its own weight. You look to see when is collapse imminent. This is because the furnace operators really don't like to have specimens collapsing in their furnace. It tends to damage the furnace. So you look to see when deflections become excessive and you think the element's about to fail, or when you start to see the element you're testing deflect rapidly, and then you might stop the test to protect your furnace. Integrity is where you have a flame that comes through the specimen. So imagine that you're testing a floor ceiling assembly. You have a fire under the ceiling that's in the furnace. So you put a ceiling on the furnace and you start the fire. And you look at the top, which would be, of course, in a real building, the floor above, and you look to see if you have any flames coming through the top. You look to see whether there are cracks and fissures that would allow these flames. And that's the time for integrity. So as soon as you see sufficient cracking that a flame can come through, that's when the specimen fails. And that's the time for integrity. Remember, you round it down to the nearest 30 minutes. The other element that you look at is what is the temperature on the unexposed side of the element? Is it hot enough that it might ignite something that's on that other side? So again, you look at the time when it gets too hot, and there are temperature criteria that you use, and that time becomes part of the fire resistance level. Now, there are some general requirements that you need to look at. The first is that the specimen that you're testing must be representative of the element of construction. So if you're testing a beam, it has to be a beam, and it has to look like the beam that you're trying to get a rating for. It needs to be made of materials and to the standards of workmanship that are representative of how it's actually going to be built in the building. So imagine that you're testing a plasterboard wall. So what you need to do is check that the fastenings that hold the plasterboard on the wall are in the same location that they will be when you build the building. So you might have fasteners every 30 centimeters in the test. Then you have to have the same type of fasteners, the same length, and the same inserted the same way in the actual building as you build it, right? So the test has to be representative of what's actually going to be used. What if it's not? Well, in that case, you're allowed to use some engineering judgment. So the Australian standard 4072 Part 1 provides some guidance and allows for acceptable variations to the tested specimen. So you're allowed to vary a little bit, but not a lot. And engineering judgment needs to be used to determine whether the actual variation is significant or not. A registered fire test laboratory might provide a formal opinion or assessment of a field application. So let's pretend that you've got something and it's a little different than what was tested. You can go to a NATA-approved lab and have them give an opinion. Now, when we say NATA-approved, we mean a laboratory where the AS 1530 Part 4 test has been approved. So an opinion from a NATA lab that's approved in something other than fire resistance testing is not acceptable. It has to be a lab that has experience with the tests that we're actually looking at. Now, there are some other strange things. One is that specimens can be tested numerous times until they get the rating they want. So let's say that you wanted a 60-minute rating, and the first time you ran the test and it failed at 55 minutes. There is nothing that prevents you from testing that same sample again, except that some labs won't redo that test for you, so you might have to go to another lab to have the test done. Well, there is one other problem with the test, and that is the results of the test have nothing to do with real-world performance. They are simply an acceptance criteria that's used as part of the building code, as part of the deemed to satisfy fire resistance level. There is no correlation with field performance, so that a 1-hour rating in the furnace does not correlate with 1 hour in the real world. So a beam that survives for an hour in the furnace could fail in 10 minutes in a real fire, or it could last all day in a real fire. It's simply a method. This 1 hour is simply a number that ranks that beam. So a 1 hour tested beam will be better than a 2 hour tested beam, all right? Will be worse than a 2 hour tested beam, but that 2 hour beam won't necessarily last twice as long as the beam with a 1 hour FRL. Very confusing, but that's the world of testing. Of course, none of this matters as long as we're dealing with deemed to satisfy. It only matters if we're trying to do an actual performance design. Performance design, you need to know what is the time to failure in the real building. How is it really going to perform? When we look at the building code, the BCA, today's BCA, talks about fire resistance in Schedule 5. And Schedule 5 has tables that lists the deemed to satisfy FRLs for masonry walls, for concrete slabs, for certain types of protected steel beams. It also has Clause 3. Clause 3 tells you what do you have to do to calculate a fire resistance level by calculation. The first is that whatever you're calculating has to be very close to something that's already been tested. The second is that your calculation must actually calculate the same things that are in the that are determined in a test. So that would be structural adequacy, structural or integrity, and insulation. Now, it may be that the thing you're testing, let's say a column, only has structural adequacy. So we test a column, we want 120 minutes, and you calculate that. The column doesn't have integrity and insulation because the column doesn't try to stop fire spread. It just is there to hold up the building. In your calculation, you have to account for the fire exposure, or for the temperature exposure from the furnace, and for the heating of the element. So you can't assume that the element isn't hot. After all, it's getting hot in the furnace. You have to look at the different features of the element being tested, the size and the shape. And you have to account for the design load. How loaded, what is the stress level in the structure? There are tools to help you. There's even an old standard, ASCE, SFPE standard 29-99, which gives you some simple calculation methods for determining fire resistance in the furnace. Again, you have to be careful because this American standard only gives you one number, whereas in Australia, we need the 3 numbers to determine the FRL. But you can use the standard nonetheless with a little bit of care. Now, we've been talking about the deemed to satisfy fire, and yet we are looking at a standard test. The problem is that for a real fire, one that's not in the furnace, one that's in a building, right? If we want to learn from the furnace and extrapolate to the real building, there has to be a relationship between the occupancy or fuel load or classification of the real building, right, and what we test to in the furnace, and I'll come back to that in a few minutes. The floor area, which is used to determine the construction type and therefore the required FRL, and the heat energy impact of the fire, right? So that's not the heat energy impact of the fire in the furnace, but it's the heat energy impact of the fire in the building. Well, this is the difficult problem, isn't it? Ingberg in 1920 developed a simplified approach for doing this calculation. He simply said, well, we've got the standard fire in the furnace. We'll look at the actual fire. And as long as areas A and area B are the same, then we can come up with an equivalent time. So it's not actually the time in the real fire, but it's equivalent time rating from the furnace. In other words, the FRL. So he did a series of tests. And he did a variety of fuel loads. Being in America, he was using pounds per square foot of cellulosic equivalent material. Now, while he was running the tests, he adjusted ventilation because he realized that ventilation into the space was critical to determine how hot the fire was and what the fire exposure was. So he had some dampers that he opened and closed to make the fire conditions as severe as possible. Here are his results. So the left-hand side of the column is the average equivalent fire load in kilograms per square meter of floor area. And the right-hand side is the FRL, or as he called it, the fire endurance in the furnace. The fire load density in that left-hand column, well, I've indicated. So for example, an office building is somewhere between the 45 and 60 minute, a shopping center between the 60 and 90 minutes, a dwelling about 90 minutes, and a library is off the chart. Here's the data that he actually plotted to develop this correlation. One might argue that the data points don't fit very well to the correlation. That's the straight lines that you see. But considering this was done in the 1920s, it's not bad, right? Can we do better? Well, we've tried, and we really haven't been able to do better since. So going back to this issue of performance-based design, this is the real world. We start by looking at a building's classification. Right? That's always the starting point in our building code. What is the building going to be used for? Or what is the section of the building that we're evaluating going to be used for? We look at the structural design. Is it concrete, steel, timber, masonry? Are we expecting that we're going to protect the structure with boards or with an intumescent coating or some other means? We look at the design fire. What is the expected fire in the space? The building code, of course, does this for us. It takes an average classification, says, all right, behind the scenes, someone decided here's the kind of design fire, and here's the FRL, or the structural fire protection, that we're going to need. But if we're doing performance design, we have to decide what is the right design fire, and we have to decide what fire protection do we need. So in the design fire, we need to know the fire load. Where are we going to get that? Well, I showed you some idea of a dwelling and a library, but where's the other information? We have to determine, what is the fire going to look like? Right? Are we going to have flashover? Of course, that's the most severe fire. Or are we going to have a localized fire? So imagine a column sitting next to a burning car, right? That burning car may not flash over the space, but it certainly heats up the column and might be a very severe heating regime. We have to then decide how hot is the structure after we've determined what the fire load is and the fire exposure. So NFPA 557 is probably the most comprehensive list of fire loads that we can use. So that's documented and that's available. And luckily, buildings in the US and buildings in Australia seem to have roughly the same kind of fire load. In determining the post-flashover fire, there is an SFPE standard. For those of you that aren't familiar, SFPE is the Society of Fire Protection Engineers. They're an international group of engineers who have developed a set of standards that can be used for these calculations. And if we then, given the fire, how hot does the structure get? So the structural engineer can do the analysis. And again, there's an SFPE standard for looking at that. So we might look at those standards. And then we say to ourselves, okay, our structure is getting too hot. We need to find a way to protect it. So one way of protecting the structure is to put some boards up. So here's some example of applications by ProMat. We can use a sprayed fire resistance material, a spray vermiculite, for example. It's kind of messy, but we can certainly do that. Or we can use an intumescent coating. And we're going to hear about intumescent coatings from our sponsor later on. The intumescent coating is, remember the little snakes that you'd lit with a match, and they would, you'd take a little disc and it would become a snake like you see on the left. It's the same thing. When you have a coating on a beam, for example, or a structural element, right? It looks like paint until it heats up. When it heats up, it expands and forms a coating. The volume therefore increases, the density decreases, and you end up with an insulating barrier that protects the element that you're protecting from the fire. Intumescent materials, depending on the product, increase in size 2 to 50 times. You can get up to 100 under the right conditions. Of course, for something to expand that much, there needs to be space. It's one of the problems I sometimes see with designers. They forget that you need to leave space for the intumescent coating to expand. There is some science behind it. You can do some calculations. And what you're interested in is how hot is the element going to get that you're trying to protect. And it's a function of the expansion factor, which is determined by how hot is the fire, how quickly does the fire heat up, how thick was the original coating, that kind of thing. So if I gave this talk a year ago, I probably would have stopped at this point. I might have gone further in depth into how intumescent coatings work, how protective sheets such as ProMat work, what are the other strategies we might use. But I thought today we would focus on something completely new and something completely different. This is the inside of an electric car. This happens to be a Tesla. And Tesla's, or any electric car, presents a new challenge for us. As you know, batteries come in different shapes and sizes, and depending on the manufacturer, a different shape, orientation, or location for the battery in the car will occur. One of the unfortunate things is that once in a while we have fires in cars, and there seems to be little difference between the frequency of a fire in an electric vehicle versus the frequency of a fire in an internal combustion engine propelled vehicle. But we have fires, and electric car fires are more of a challenge and a little bit different than the fires we're used to. They tend to continue after you think you've extinguished the fire. And that's because we have what's called a thermal runaway condition, where the battery cell sort of has a life of its own. It's a bit of a challenge to determine when this is occurring and how to manage it. In some cases, the challenge is for the brigade. In Germany, they've taken one interesting approach. There's one town where they built a special purpose truck, and they put a shipping container on the truck with a crane. And the concept is, if there's a vehicle fire, they pull up to the vehicle, use the crane and lift the vehicle into the shipping container, and they fill it full of water. That puts the fire out and stops the thermal runaway. There was a fire in the United States where, due to a collision on the road, and the brigade came, and it took them 4 hours to extinguish the fire. Now, they had the fire out in half an hour or so, but then it reignited and reignited and then reignited. It drove them insane, and they used a lot of water, and there was a lot of smoke. But this was outdoors, and they were able to manage it. The fires look like any other car fires. Aluminium components melt, other low temperature components melt, batteries burn, and the like. Electric cars have different components. They look different than your internal combustion engine car. The brigades need to learn what they are so they can learn to manage the fires. And it's a challenge as new electric vehicles are developed and produced. They have different designs, and it's something that all brigades need to learn how to manage. In Australia, we either have or will have a whole variety of types of electric vehicles we'll be able to buy. Scott Morrison has promised that we're going to have lots of charging stations. We're starting to see distances of over 500 kilometers between charges. So all of a sudden, electric vehicles are becoming more and more realistic for the Australian market, and we're going to see them more and more. So by 2050, CSIRO has suggested that 100% of our vehicle fleet will be electric, or if not electric, then it will be alternative fuels such as hydrogen. So this presents an interesting problem. The electric vehicle is something new. Our building code is based on motor vehicles from, well, really from the 60s and 70s. The code is based on vehicles that were mostly steel with, the rubber from the wheels and the petrol. But of course, the petrol was in a steel tank. And often vehicle fires didn't involve petrol. It involved the tires, the hoses, even the cooling fluid. but these are known fires and they were contained within a steel container. Today's car has aluminum, it has plastic, it's a different beast. So forget the electric vehicle issue. The modern car is very different from the car that our building code is based on. The batteries, though, they're a change in fuel. They're a change in how things burn. So when you have a petrol fire, it only happens when the tank fails. There's a rupture disc that pops out. Petrol flows away from the fire. It's easy for the brigade to manage. They know that's going to occur. But with an electric vehicle, the battery stays inside the car and keeps burning and burning. And the brigade tries to put it out and the fire keeps burning. It's a bit of a challenge. Now, the building code talks about the risk by looking at the classification of the building. The classification for a car park is class 7A. So when we put a car in a building, right, we put it into a space in the building that has a classification of 7A. What is 7A? So the definition from the code is a car park means a building that is used for the parking of motor vehicles, but is neither a private garage nor used for the servicing of vehicles other than washing, cleaning, or polishing. It doesn't talk about what the fuel is. It doesn't talk about how large the fuel is, because when the building code was written, most motor vehicles were very similar in how they burned and how they were made. So if we look at class 7A, we see that under the deemed to satisfy provisions of the building code, that it is required under deemed to satisfy to have what's called type A construction if the building is 4 or more stories in height. So imagine that you have a building and the first 2 levels are parking, and then you have a 10-story office or apartment building above. That building would be required to have type A construction. Shorter buildings, therefore ones that have less of a risk, have a less severe construction types B or type C. But we'll just look at type A for discussion purposes. So when you have type A building, the fire resistance level, and remember this is just for deemed to satisfy, the fire resistance level is given by a table. And so for the load-bearing walls bounding a public corridor, etc., the FRL is 120 dash. That is, the structural adequacy is 120 minutes. Integrity and insulation are 0. Actually, they're not even measured. That's what the dash is for. An internal beam to a car park or a truss or a column, so the structural elements that hold up the rest of the building, they'll also be 120 dash. The floors, on the other hand, so this is for example, think of the floor separating the car park from the apartment building above or from the office building above. That's required to have both 120-minute structural adequacy, but also 120 minutes integrity and insulation. So for 2 hours in the furnace, the floor is supposed to prevent the fire from spreading from below to the space above. But is 120 minutes enough? Good question. We have a new type of fire, this battery fire, that burns and burns and burns and is very hard to extinguish. The peak heat release rate is about the same as an internal combustion engine, but it's harder to control that fire. This is a fault tree from NFPA 550, and this is sort of the general part of looking at failure analysis in a space. In terms of managing the fire, there are 3 ways we can do it. One is control the combustion process. One is to suppress the fire. and the other is to control the fire by construction. Well, we can't really control the combustion process. We can't say you cannot put electric vehicles into our building, not if you have a car park. Controlling the fire by construction is where the fire resistance level comes in for the deemed dissatisfied building. Well, we could look at that. We could suppress the fire. So here we either have automatic suppression or we have the fire brigade. Now, often the larger car parks, 40 cars or more with limited ventilation, are going to have an automatic sprinkler system installed. The problem is that automatic sprinklers seem to have little impact on EV fires. Based on small-scale tests, they barely touch a battery fire at all. Do we need something else? Is there another type of system? Good question. We'll have to think about that. We could just let the brigade manage the fire. Now remember that I said that when a fire is outdoors in California, they had the problem where it took 4 hours to put the fire out. Imagine the brigade coming to your building, going into your car park, maybe it's 2 floors below the ground, and trying to put the fire out. Normally, we'd expect that the sprinklers would be helping them, but in the case of a battery fire, they don't. So the brigade is faced with a real problem. One, it's a severe fire. And two, you need a lot of water, hours and hours of water supply to actually manage. So no, we can't actually expect the brigade to manage these fires. One thing they could do is, of course, move the car, pull it out of the car park. But many of our car parks are built so that we can't actually get a tow truck in. The ceiling height's not tall enough. Or we have to get very close to the burning car. I'm not sure how we can manage that, but maybe we need some sort of a robot that we develop or design for that purpose. Well, that's something we're going to have to look at. The other thing we have is this fire is now burning. It's pretty intense. Imagine if you have an existing car park and you want to put a charging station in so you have a place for your electric vehicle. Where do you put the chargers? On a wall, perhaps, or on a column? Oh, a column would work well. You might put 2 or even 3 cars parking next to that column so it's easy to plug them in. All of a sudden, you've surrounded that column with an unusual heat source. Is the FRL of the column sufficient? I don't know. Let's look at that next. So the answer is somewhere in the world of research. We're going to have to do some research at this problem. Can we manage the heat release rate of this car park, of this electric vehicle, with some sort of a suppression system? We know automatic sprinklers aren't enough. Can we use something new, like low-pressure water mist? So water mist is like sprinklers, except the droplets are very, very small. And so they heat up very quickly, and they expand rapidly, and they get into spaces almost like a gas suppressant system. That might work, and there's some data and some tests to show that water mist may in fact be the solution for an EV fire. The problem is that we don't usually trade fire resistance level for automatic suppression. We don't usually say, well, if you provide me with a suppression system, I no longer need to worry about a building collapse. Our general philosophy is that we use both. We have a belts and suspenders approach for both suppression and protection against collapse. So how can we determine a fire resistance level? What do we do? The first thing we need is some experimental data. We need to know, how do these cars burn? We need to burn some Teslas. We need to burn some Volkswagens. We need to burn your favorite Volvo, all the new electric vehicles. We have to determine how hot are the fires? What is the heat flux to this space that would be equivalent to the furnace that we are going to be running some tests in? That's what Ingberg did in the 20s. We're going to have to do something similar today. We then are going to have to do some advanced calculations to determine how hot are the structural elements when exposed to that fire. We're going to have to do some sort of probabilistic assessment, right? Certainly something we can do, but expensive, and we don't actually know how to do that right now. But we can figure that out. We have the tools. We just have to apply the tools. And then from that, we can back calculate what is the appropriate fire resistance level. And we can use that for design. Maybe we can even look at what if we don't allow those 3 cars around a single column and we only allow 1 car? Can we control where we put our vehicles? Can we redesign the shape of car parks? So for a new car park, we can redesign the shape. For an existing one, we probably can't. In any case, it's sort of a performance solution that's a little bit unusual. How do we control where people put their cars? Maybe an interim solution works. The highest FRL we ever use is 240, 240, 240. Maybe we do that. But that's twice the requirement in the current building code. So we have all these existing buildings, and all of a sudden, we need to increase the FRL. We could rebuild the structure. In the case of concrete, we just have to take the column out and put a new one in. That doesn't make sense. Sometimes we have timber floors in our car parks. How does that happen? Well, sometimes there's a performance solution that allowed unusual construction. What do we do with a timber floor? Maybe we have an existing situation where there's a column or a beam that has fire-resistant boards protecting it or has intumescent coating. Perhaps all we need to do is improve on that. We should ask ProMat and Dulux for how to do that. They have the knowledge and the information so that engineers can apply their products in a retrofit situation. So in summary, we have a new problem. It's quite different. We have some products that might be able to be used both for new and existing buildings. I'm particularly excited about existing buildings where we're going to have to fix the problem. But there are no standards on how to do this. We don't actually know how to calculate. We do know how to calculate the heat transfer, but there's no standards on an appropriate method. Performance design becomes the only option. And yet we really need a deemed to satisfy approach. We need a simple way to do things. Otherwise, well, it'll be just too expensive to fix. So the next few years, I think we're going to see a substantial amount of research in this area as we move forward and try to find a way out of the dilemma. It's going to require cooperation by practicing engineers, equipment manufacturers, manufacturers of protective coatings. It's going to require a change to our codes and to our standards. It's going to require university research. We're all going to be busy for a long time while we look at this new problem. But it's exciting, and I look forward to doing that and being involved as we develop a solution to this new real-world problem. Well, that brings me to the end of my talk. I want to thank you very much for your attention, and I understand I'll be able to take some questions, and hopefully we'll have some good answers for you. Thank you very much.
Thank you, Jonathan, for your insights. I'd now like to welcome our second speaker, Jeff Boone. After working as a land surveyor for almost 10 years, Jeff made the move to ProMat Australia in early 2003. His first position was Technical Support Engineer for New South Wales, a position he held for 6 years, working closely with engineers and architects, providing solutions for their passive fire requirements. Over the coming years, Jeff has had numerous roles within the Australian business, from managing product segments, introduction of new business units, as well as country manager of New Zealand. In 2016, Jeff became the National Commercial Manager for ProMat ANZ, a position he holds to this day. Jeff has a very keen interest in all aspects of passive fire protection and is very passionate about the industry. Please join me in welcoming Jeff Boone.
Thank you. Firstly, my name is Jeff Boone. I'm the National Commercial Manager for Promat ANZ, and today I'm here to present on the topic of structural steel protection with a focus on using boards and spray systems. Firstly, what is fire? Fire is essentially a rapid oxidisation process accompanied by the evolution of heat, light, flame, and the emission of sound. It can be useful, but too often it is unwanted. Fire may affect the life safety, property, or contents of a building. The impact on fire on these three will vary according to the purpose of the building. During combustion, a series of very rapid chemical reactions take place, which require the following elements to be present. Fuel, the fire load, flammable gases, flammable liquids, and flammable solids. Heat, the ignition source, hot surfaces, electrical apparatus, static electricity, smoke, and naked flames. And oxygen, the ventilation, always present in the air. The three essential elements are known as the fire triangle. The oxidisation process requires all three elements to be present. To extinguish the fire, one of the elements needs to be removed, whether that be fuel, oxygen, or heat. This is an old video, but a good video. It shows how quickly a fire can spread in a small room and shows how important fire compartmentation is in multi-residential living.
But since most people's houses may have a 8-foot or a 10-foot ceiling, what that means is that those flames are going to hit the ceiling, roll across the room. The heat that's now spread across the ceiling is heating up other things in that room, furnishings, carpet, whatever, and you have a very rapid fire development in the room.
When a fire grows unchallenged, everything that will burn ignites. In this case, only 33 seconds after the Christmas tree caught fire.
The following pictures are from an actual building fire in Madrid in early February 2005. The pictures show the unprotected steel columns in the upper section of the building have collapsed. In the lower sections, the structural steel was protected with Promat board systems, and these have prevented collapse. However, in the areas where protection was not complete, the steel profiles have distorted severely. Fire protection. There are two types of fire protection. Firstly, there's passive fire protection. These are systems that don't require power and water to operate. Systems such as structural steel protection, partitions, ceilings, ducts, and penetration seals. The second is active fire protection. These are systems that do require power and or water to operate. Systems such as smoke alarms, fire alarms, emergency lighting as a few examples. Both are required to work together to create a safe building. It is no good having one and not the other, as it is about life safety. The role of passive fire protection and fire protection in general is to ensure the safe escape of building occupants and to give firefighters the time to rescue occupants. Fire protection is also about property protection and preventing economic damage. Structural steel protection. Steel loses its load-bearing capacity when heated above certain levels. Loss of load-bearing capacity means the potential collapse of structure is greatly increased. There are a number of ways to protect structural steel. This can be done with fire-rated boards. There are a number of different solutions available in the Australian market. Steel can also be protected by vermiculite sprays or intumescent coatings, which Roger will go into more detail after my presentation. The following slides show pictures of structural steel after a fire. The pictures are of a building fire in Sydney earlier this year. It was a new build, and the sections of the building had not been protected by vermiculite spray. The fire started due to welding slag falling on pallets of combustible material. These were large sections, 900 WBs, and as you can see, they've buckled like spaghetti. Steel structures are a growing area in modern building design. Therefore, structural steel protection is required to preserve the structural adequacy of a building in the event of a fire. A building must have elements which will, to a degree, maintain structural stability during a fire, as per NCC Volume 1 CP1. In order to meet these requirements, the load-bearing elements of the structure must be capable of withstanding the effects of a fire for an appropriate period of time, without stability. There are three main solutions for protecting structural steel in the event of a fire. Firstly, there are board and encasing systems. Secondly, you have cementitious spray systems. And third, you have intumescent coatings. Board and encasing systems. There are a range of different products available in the market, from fire-rated plasterboard to Promaxon technology boards, such as the boards that Promat offer. These products are dry fixed around the structural steel using fixings such as screws or staples. The thickness of the boards can range from 15mm up to 65mm, depending on the steel size and FRL required. There are spray systems. These are the most common form of steel protection available in the market, vermiculite-based, and is used for internal applications. There are also cementitious-based spray products for external use. These products are applied by a machine such as a Putzmeister S5, and thicknesses can range from 10mm up to 60mm, depending on the steel size and FRL required. Limiting temperature. AS 4100 clause 12.5 recognises the concept of a limiting or failure temperature to a steel section. This represents a temperature at which the member would fail irrespective of the amount of protection. It uses the concept of load ratio as a measure of applied load that a member can resist at the time of the fire. In Australia, a default conservative value of 550 degrees C is used for four-sided protection, whilst a failure temperature of 620 C is applied to steel beams in composite with a concrete slab. Section factor. What is section factor? Section factor is used to determine the rate of increase in temperature of steel cross-section. AS 4100 uses a notation ESA over M, but the use of the terms HP over A and AV are still prevalent. There is a relationship between the two, so that a HP over A can be converted to ESA over M and vice versa. A steel section with a larger perimeter will receive more heat than one with a smaller perimeter. The greater the cross-sectional area of the section, the greater is the heat sink. Therefore, the section factor is a measure of the rate at which a section will heat up in a fire, and the higher its value, the greater thickness protection is required. Thin sections heat up faster than thick sections. An equivalent size. The larger the section, the less protection is required. All tested systems have a maximum section factor they can protect. If the member's section factor exceeds this, it can't be protected adequately. Any member size with a HPA above 260 will be limited to options for structural steel protection. Calculating castellated sections. To calculate the protection requirements for a castellated section, the thickness should first be obtained based on the original section and then increased by 20%. This is due to the temperature of the protected castellated members increases at a slightly faster rate than conventional sections. This does not apply when looking at intumescent coatings though. Composite beam protection. If a concrete slab is constructed using profiled steel deck, voids are created between the deck and the top flange of the beam. If the void is left unfilled, two potential problems arise. The rate at which the heat enters the section is increased, and the increase in temperature causes the section to lose its strength at a faster rate. For metal decks such as bond deck or con deck, with smaller voids, nothing additional is required. For larger voids, they will need to be filled with the protection material used to protect the steel section or filled with high-density mineral, unless there is test evidence showing that this is not required. If the beam falls on a compartment barrier, then all openings must be blocked no matter what the size. Beams with web penetrations. Where a beam has a penetration cut into it for surface to pass through, this will affect the performance of the beam. The thickness of the material around the penetration needs to be greater than that for the rest of the beam. There is a method to calculate this in AS 4100. The increased thickness should extend for 300mm on all sides of the opening, or to the full depth of the beam if it is less than 300mm. If a beam is in line with a compartment wall, then the opening and the surfaces will need to be fire stopped to maintain the integrity of that compartment. Connections. Plates, welds and fixings used to connect sections together require the same thickness of protection applied to the smallest member that is connected to. When non-fire rated sections connect to a fire rated member, a 300mm coat back of the same material is required to ensure heat transfer is minimised to the protected member. Fire testing and assessments. Testing. AS 1530 Part 4, Section 5 and 6 covers fire testing of steel beams and columns. Only structural adequacy is required. Criteria of failure is either collapse or when a certain amount or rate of deflection of a member has been exceeded. Results from a single test can be applied to larger steel members provided the same thickness and material is used. Assessments. As you can imagine, it is not possible to test every different size of steel, so AS4100 has a process whereby selection of various size members can be chosen and from the data generated can be used to come up with a table of thicknesses for a variety of section factors, time periods, and critical temperatures. At least 9 members need to be tested, and the data is then subject to a regression analysis which will produce information for the thickness tables. Board systems. There are numerous options for structural steel protection using boards from plasterboards to Promaxon technology, the systems that Promat offer. Board systems provide FRLs from 1 hour up to 4 hours, and thicknesses can vary from 15mm for 60-minute protection up to 65mm for 4-hour protection. For the Australian market, systems need to be tested to AS1530 Part 4, 2014 and AS4100. Structural steel sections requiring 2-hour protection can be protected by a single layer of board, as shown in the slide, Promatec 250, thicknesses up to 30mm. Smaller sections such as SHSs and RHSs with a 5mm wall thickness generally require 35mm thickness for 2-hour protection. The fixing detail is rather simple. Boards are butt jointed and screwed or staple fixed at 150mm centres, with cover strips located between the flanges at 600mm centres for UB and UC cladding. For SHS and RHS, boards are fixed hard up against the steel section and fixed at 150mm centres. There is no fixing to the steel section itself. Any gaps between board butt joints that are less than 2 to 3mm do not require a fire-rated seal. It is always recommended to apply a fire-rated seal where the board butts to the underside of the concrete slab. Promat has boards available for 3 and 4-hour protection. It's the same fixing detail as applied for 2-hour protection. However, thicknesses range from 20mm up to 65mm. Using boards to protect structural steel is a cost-effective solution. It is a dry trade, unlike sprays, and can achieve FRLs between 60 and 4 hours on large range of steel sections. Boards are easy to fix, can be profiled around difficult designs, and can be set and painted for an architectural finish, as shown in the pictures in the slide. Here are a few pictures showing Promat boards being tested for structural steel protection. As you can see, the beams are loaded. There is a picture showing the junction between the beam and the wall. Once a test is underway, deflection does occur due to the loaded beam, and as you can see from the red picture, gaps can open up in the cladding. Spray products such as Cafco 300 for internal steel protection are vermiculite and gypsum based. They are lightweight coating that provides very effective and efficient fire resistance with minimal thicknesses to steel, concrete slab upgrades and metal deck upgrades. For external applications, Fenderlite M2 should be used, as this is a cement-based product, unlike Cafco 300. It is also used largely in the oil and gas industry. For semi-exposed applications, Mandalite CPT should be used. It is a hybrid of Cafco 300 and Fenderlite and is ideal for perimeter edge beams. The advantages of spray systems is that they are cheap, lightweight, well accepted by industry and perfect for hidden steelwork. They have stood the test of time with over 30 million metres squared of steel being protected. Thank you. This concludes my presentation.
Thank you, Jeff, for your insights. I'd now like to welcome our third and final speaker, Roger Todler. Roger is a technical sales and project management specialist with 11 years in the Intumescent industry across South Africa and Australia. Roger graduated from Technikon, Witwatersrand in South Africa, with a diploma in mechanical engineering and worked in an engineering manufacturing business for 5 years. In 2010, Roger brought his methodical mindset to his next role in PPG protective coatings in South Africa, and his key responsibility was to support the specifications, sales and applicator training for both cellulosic and hydrocarbon intumescent coatings. Roger has been working in the protective coatings and intumescent space ever since. During his time with Dulux, Roger applied his project management and technical customer service skills as a technical sales representative in Newcastle and is currently the business development manager for Intumescent for Dulux Protective Coatings. Please welcome Roger Tobler.
Thank you for the introduction. And today I'm going to be speaking on the durability of intumescent coatings, and we're going to look a little bit at the complete systems around intumescence. So in our introduction, we're going to talk about selecting the correct type of intumescent for the environment that we find the building in. Firstly, the majority of structural steel is in a building. It's located inside in a dry environment. Very little steel is usually on the outside and exposed to moisture and rain. Also very important is to consider the exposure during the construction phase. Is the steel going to be wet? Is the intumescent coating going to be exposed to moisture during the time until the building's sealed? Other considerations that play a really important part in selecting intumescent is water-based intumescents and 100% volume solid products have very low VOCs. If you want a fast drying and a durable coating that can be yard applied, you'll look at a different type of coating, but that's another consideration you'd have in selecting your intumescent. So let's move on to the types of corrosion categories and which intumescents are best suited for each environment. First up, we'll look at water-based. Mostly used in C1 to C2 corrosion environments. These are really dry, not a lot of UV. There's no moisture in these environments. Sometimes intumescent coating companies will specify them up to a C3 environment, but largely not exposed to moisture. Then we move on to solvent-based intumescents used in a C1 to C3 environment. The challenge here is the solvents and the VOCs frequently, but slightly more durable than you'll find a water-based. Some intumescent companies with 2 top coats will be using these externally. And then the most durable of all epoxies, they are intumescent coatings that are chemically cured. Epoxies really handle exposure to the environment, and they're really durable coatings. You'll find that an epoxy intumescent can be used without a top coat and without a primer. They can be applied directly to blasted steel for a C1 to C3 environment. And that eliminates a lot of additional time and cost associated with applying those additional coatings. The above is general classifications for intumescent coatings, and different manufacturers will use different rules, but this is a general rule that most companies will stick to. Top coats do improve the durability of the intumescent. So the shape, the orientation, the location of items does have a bearing on how much moisture those items will be exposed to. And we should consider these when looking at externally located items. Will the steel be exposed to direct rain or moisture? Is it going to be under roof, or is it going to be totally exposed? And what sort of climate or environment is that building in? Is it close to the ocean? Is it in a really dry environment? This exposure to moisture, or any potential exposure to moisture, is it a regular occurrence, or is it a once-off? Is it going to happen frequently? That's also to be considered. Looking at the shape and size, a smooth vertical column, well, that's going to allow moisture to run off. There's no risk of any moisture pooling or ponding, and the coating will run down the durable top coat and it will run away. What could be more concerning is horizontal beams, where there's likely to be pooling and ponding of moisture. You find a horizontal surface, the water just gathers there, and that's not good because it's going to find a pinhole, or it's going to permeate through the top coat into the intumescent. And lastly, consider, have any holes been drilled, brackets mounted? Has there been any welding? Has the integrity of the top coat been compromised? And when the integrity of the top coat is compromised, well, the intumescent is now potentially exposed to moisture. Unless it's an epoxy intumescent, solvent-based and water-based, they can be damaged by moisture. So talking about intumescent systems, the first coating to be applied is the primer. It's applied onto abrasive blast to clean steel. Typically 75 microns of primer is more than sufficient, provided you've got the correct intumescent system. You're not trying to provide a corrosion protection system by increasing the primer thickness. This is really the coating that's going to keep the steel dry, clean, and in a suitable condition to receive the intumescent. The primer does need to be clean, and often on a construction site there may be cement and a whole lot of debris and contamination on top coat. So yes, you are going to have to wash it, and this may require a good abrading before you apply the intumescent coating. The intumescent coating will be the appropriate intumescent coating for the environment. Water-based C1 to C2, solvent-based C1 to C3, on epoxy if it goes up to a C5 environment. Top coats, they're going to add durability to your intumescent, and the other function of the top coats is to add a gloss level and to give you the required color. The most durable top coats that can be used with intumescents are polyurethane top coats. They're two-component products. They give you a good barrier to moisture. However, we must remember they're thin. They're typically 50 to 75 microns. If you're putting a thin coating on, you may miss some edges on corners. So by applying two coats, you reduce the risk of any uncoated areas. And that's important that the top coat cover the intumescent fully. It's also very important that the top coat doesn't inhibit expansion of the intumescent when there's a fire. And we'll talk more about this in the next few slides. So we're going to show you a few pictures of intumescents that have been tested in a furnace, and we've tested intumescents in conjunction with the top coat. So the first picture there shows you an intumescent applied at 1,000 microns before the test, not exposed to heat, and the top coat is applied over it. The second photograph, same panel, and this is post-exposure to heat in a furnace. There's a thermocouple attached to the back of the plate. The plate is heated up to 500 degrees Celsius and the time recorded. So now an evaluation is done, and the evaluation is both a visual inspection and a comparison to a panel that wasn't top coated. And the expectation, the requirement is that the panel with the top coat performs at least to 85% of the panel without the top coat. This is a test that's described in a European technical assessment. The panels are subject to a small amount of weathering before this, then the furnace test, and this European technical assessment then states that there's an assumed working life for that system for a 10-year working life. It's really essential that the top coat doesn't limit the expansion of the intumescent, and without any testing of the top coats by the intumescent supplier, this can't be guaranteed. So this is really essential that top coats are tested. The next test for evaluation of intumescent coating systems is a dolly pull-off test, and this is to check the adhesion. And the dolly pull-off test is used because it's a thick coating. Hatch and cross-cut tests are used for thinner coatings. So using the industry norm, we'll have a look at the dolly pull-off test. So these little dollies are glued onto the coating system. Once the glue is fully dried, they pulled off, and the force that they pulled off with is measured. So we find that water-based products typically achieve 2 to 4 MPa. Cohesive failure that is listed on the slide there is the failure of the intumescent. So it's not the primer, it's not the top coat, but it's the intumescent that gives way. Looking at solvent-based intumescents, you get similar values, 2 to 4 MPa, and again, it's cohesive failure in the intumescent. So the intumescents are designed to expand when they're exposed to heat, and as such, they don't have great cohesive strength under normal atmospheric conditions. Enter the exception, and these are the epoxies. And what you find with the epoxies that they're chemically cured, they're really strong coatings, and you find far larger adhesion values. And often the failure here is no longer in the intumescent. It's the primer, the top coat, that starts to fail because the intumescent is much, much more durable than a solvent-based or a water-based product. This testing gives us an indication of the strength of a coating, and that strength is giving you some indication of the durability that you can expect from a product. The adhesion test is also telling you a little bit about if the intumescent sticks to the primer and if the top coat sticks to the intumescent. So moving on to the next form of testing that's done on intumescent coating systems, complete systems, primer, intumescent, and the top coat. On the left here, we see the 3 coatings applied, and then they're exposed to a severe environmental testing regime of a high humidity with salt and varying temperatures. And the system on the left is a water-based system. So it's an epoxy primer, water-based intumescent, and a polyurethane top coat. And this is 200, these panels had 200 hours of exposure. You'll see the one with a scribe at the top, that's a X mark back to bare metal. That's had the most amount of damage. And you can see that in the flakes and the cracks in the top coat. But all through you can see this product has been compromised. And we're testing a water-based intumescent far beyond the C2 environment here. So it's to be expected that it'll fail really early because it's tested where it shouldn't be going. On the second slide, we've gone to the opposite end of the scale. We've tested an epoxy intumescent. We've gone to 2,000 hours of testing here. That's 10 times what the panels on the left were subject to. And you can see virtually no blistering, no delamination, no undercreep. And that's with an epoxy primer, a epoxy intumescent, and a polyurethane top coat. So really good results. We then tested the intumescent on its own to understand how durable the intumescent is without a top coat, without a primer. And we got similar results to the panels on the left with the epoxy primer and the epoxy top coat. So it just confirms that epoxy intumescents are really durable to moisture exposure. So what we have done, we've evaluated a few different top coats. So it's not just one top coat. We evaluate all the top coats that we use and specify. We're trying to understand the intumescence coating durability by testing only the intumescent panel. The X represents damage or compromised systems. So the fact that the uncoated system performs so well gives us a lot of confidence in that even if there is damage, an epoxy system will really show good longevity. The last thing I need to say is once these tests are completed, usually an adhesion test is done just to see if there's any anomalies to the adhesion test that was done previously. So on the exposed panels, adhesion tests are done, and again checking that there's good adhesion values. So as I mentioned, 2,000 hours for the epoxy, and that's the 2 panels on the right. You'll find that solvent-based, there's some literature out there that speaks about solvent-based intumescents, and they typically get 1,000 hours with exposure to severe environmental testing, and then they start to show some undercreep. So they do fare better than the water-based, but they don't compare to the epoxies. So the last point I need to make is life expectancy and warranty. So we've looked at a little bit of technical evaluation of a product, and the durability and life expectancy is going to be linked to an evaluation of a complete system. So the performance of the coating system will be based on this evaluation. And once you know what your system can achieve, then you can talk about a warranty. The warranty can't come before durability and life expectancy. So the warranty is based on the full study of the full coating system and understanding the durability and the system and the coatings compatibility with each other. Thank you for your time, and I trust that this has been an insightful time of learning. Thank you.
A huge thank you to our speakers this afternoon, Dr. Jonathan Barnett, Jeff Boone and Roger Tobler. As always, it's now your turn to get involved, and our speakers will come together to take questions from you. If you'd like to submit a question, could you please do so via the YouTube chat box? If you'd like to provide your name and where you're watching from, that would be great, but you don't need to. Thank you to everyone who sent questions through on registration. We might begin with some of those. The first question I have is from Pahir, and Pahir's in New South Wales. Good evening to you. Asking to you, Roger, I have specified intumescent paint which has been accepted. My concern is that it is not covered in the NCC. Intumescent paint, intumescent putty for sealant is mentioned, but not intumescent paints. Can you please offer any insights? Thank you, Pahir.
Yes,
Roger.
yes. The NCC refers to standards, and in those standards, intumescent coatings are covered. So although not mentioned by name, they are covered.
Thank you for that. We might stay in New South Wales, and Jonathan, we have a question from Lana. Good afternoon to you, asking, what are the limitations to the application of an intumescent coating with regards to achieving a performance solution under the BCA facade combustibility provisions? Given an example, can timber cladding simply be painted over? Thank you, Lana.
Well, no. Look, you can do a performance solution for anything, but the question is, can you develop a reasonable one? The challenge is with a combustible external wall, for example, you have cracking, you have weathering. You heard Roger talk about the issues of weathering with intumescence. And the bottom line is that I don't see how you can develop a performance solution, not with the products that we have now, not with combustible external walls.
Thanks, Jonathan. Does anyone else want to add to that, or we're good? Jeff, we have a question in from Victoria, from Charbel. Good afternoon, Charbel, asking, what is the general limitation of intumescent coatings in terms of FRL, i.e. when to use intumescent versus vermicellulite or fire-rated cladding, practical rules of thumb, etc. Thank you.
Yeah, hi, Charbel. Well, look, when it comes to intumescence, rule of thumb is 2 hours is the maximum they can achieve. The way I look at it is that if the steel needs to be exposed, there's nothing hard up against the steel, well, then use intumescence. If the steel is going to be hidden with a suspended ceiling or behind some type of partition, then I would recommend vermiculite spray. And if you needed another architectural finish where the steel is going to be exposed and there are going to be elements hard up against the steel, you can also go down the cladding route of a board system. Thanks.
Thank you for that. Back to you, Roger. We've had a question, this is coming from South Australia, from Krishna. And Krishna is asking, are there any ill health effects due to the application of intumescent coatings? For example, the coating becoming loose over time and infiltrating a ventilation or air conditioning system, which then gets passed on. Great question, Krishna.
I think the biggest concern with health risks with intumescent coatings would be solvent-based intumescents, where you'd have VOCs released. And that's only during application. Once the intumescent coating is cured, there's going to be little chance of it detaching or coming apart. Most often, there's a top coat for color purposes, and that further seals the intumescent coating. So there shouldn't be any health risks from cured intumescent coatings.
Thank you. We might just stay with you, Roger, for the next question, which is coming from Joel, who's based in Queensland, asking, when testing for DFT, is the maximum thickness that critical to protective coatings' overall performance?
So yes, maximum DFTs do matter, and what happens is coatings are porous to a certain extent. So if you have a thicker coating, you have a thicker barrier. It takes longer for the moisture to permeate through the coating. So when you've got a barrier type coating, yes, the thickness does matter. It slows down the migration of moisture. If you've got a zinc primer, you've got more zinc that's able to give you galvanic protection for longer, it takes longer to be consumed. How to bring this across to intumescent coatings? Really, the top coats are a barrier, the polyurethanes, and they typically applied 50 to 70 microns per coat. So you've got a very thin coating giving you a barrier protection for your intumescent.
Thank you for that. We've had a question from Robert, good afternoon, who's in New South Wales, and direct to Jeff, and I'm wondering if Jonathan maybe also want to comment. But starting with you, Jeff, Robert's asking, what are some of the techniques to inspect of pressure equipment piping under intumescent coatings? Thanks, Jeff.
Look, I might actually pass this off to Jonathan, because this is sort of, I guess, a bit of an area out of my expertise. When we look at intumescent coatings from a ProMat perspective, we actually don't have data on pressure pipe and pressure pipe equipment. So maybe maybe Jonathan might be able to alleviate more on this one for me, please.
Actually, before we started our conversation, Roger talked about some personal experience with this. I'm going to handball to Roger.
Roger.
I'm going to run away just now. It was really on vessels that we were talking about. So piping is a little bit more tricky, but it can be done. And it was on hydrocarbon intumescents, a little bit different to structural steel. And we'd come up with preformed moldings to the same thickness of the intumescent that was sprayed. And these were put in little inspection hatches flush against the steel. They fitted perfectly in between, and they were used on circumferential welds and longitudinal welds on a vessel, so that you didn't have to break away the coating to do an inspection on the metal. So I guess on a hydrocarbon scenario, you could do that on piping for small areas, not for the full area. So you could have dedicated areas that you choose beforehand that you want to do this on.
Thank you for that, Roger. And just staying with you, a question to Jeff, actually. Apologies, that has come in from Harriet. And Harriet is asking you, Jeff, does the default temperature of 500 degrees Celsius for steel members mean that steel members with lower limiting temperatures, e.g. 450 degrees Celsius, cannot be protected with these methods? Thank you, Harriet.
Hi, Harriet. No, definitely not. When you look at a lot of our test reports, we have a range of critical temperatures, and just off the top of my head, I know this one today because I was dealing with an engineer today about it. With our vermiculite spray systems, in our report, we have critical temperatures up to from 350 degrees up to 750 degrees. So we can definitely cater for different critical temps outside those default ones of 550 and 620.
I might add, remember that in the NCC A2.2, when you are looking at results, it's important that you look at the test reports. And that's really what was just being talked about, is what they have in test reports are often different than what's in the sales brochure. And as engineers, we're not actually allowed, in accordance with the NCC, to make decisions based on a sales brochure. We're actually required to look at the original test report. So I think that, there's a plethora of information there. We have to ask for it, and the good manufacturers have no difficulty sharing it with us.
Thanks, Jonathan. Thank you for that. Roger, a question from Joel is asking, is there any decrease in intumescent protection when the thickness has been increased past recommended dry film thickness? Thank you, Roger. Good question, Joel.
Joel, the top coats are tested by the intumescent manufacturer, and you'll test the specified coating thickness. So if the Dulux specification were to read 2 times 60 microns, it'll be a total of 120 microns of film board. If you apply it above that, it hasn't been tested. And it may totally impede the intumescent, or it may partially impede it, but you won't get the tested benefit of the intumescent. So you'll have a substandard system that may or may not work fully. So we don't recommend applying more than the full specified thickness. If it's applied too thick, the only thing you can do is remove it by abrading it.
Thank you for that. And Roger, just staying with you, we've had a question around, are there any tested systems where the intumescent is covered with a layer other than the top coats that is intended to burn away to enable the intumescent to expand? For example, timber veneers.
So timber intumescents are tested with a top coat in a furnace as part of the evaluation of the full system. They're not tested with cladding, they're not tested with timber boards, they're not tested with insulation. There may be some ad hoc testing, but the certification that's tested and approved by the third-party labs is purely with the intumescent, and then top coats are tested. No boards. If you're going to test timbers, you're going to have to test every single type of timber. It doesn't mean you approved for one 6mm board that the next 6mm board will burn away before the intumescent. So it becomes very tricky to evaluate every single possibility of everybody's cladding, everybody's timber boards. So no, they're not tested.
Thank you. A question that's coming from Amiga, and this may probably be one for Roger again, but asking, is intumescent coating application limited to steel, or can it also be used on timber, which is coming up quite a bit?
So there are different types of intumescent. There are different types of intumescent. Dulux currently supply intumescents for structural steel. We don't supply timber intumescents. There are a few companies that do timber intumescents, and that they are different intumescents, and they are available, but not from us.
Thank you. Thank you. We're sort of running out of time, and today's Thought Leaders series, we're talking about design and application of intumescent with protective coatings. And for some closing remarks, I just want to, based on your presentations today, is what do you think the trends are? You know, what are going to be the drivers of change in your particular area over the next a few years? And Jonathan, can I start with you? You know, what do you think the priorities are, and what is going to drive these changes that we should be getting to?
Well, look, I think that we have new fuels, new challenges. I talked about electric vehicles. There are other new challenges that will come along. There was a good question about, can we protect external walls with intumescence? No, but are there other things we could do? And this is where, you know, manufacturers, as they identify a market, the chemical engineers out there will develop a solution. So I think that things are exciting. The future is there. There's more research being done every day. I started working with intumescents in the 90s and doing computer modeling of them. But today's modeling is so much superior to what I was doing. And that by being able to model, we can develop performance solutions. We can go beyond tested systems. Well, at least we can interpolate within tested systems. We probably can't extrapolate yet.
Thanks, Jonathan, and thanks for being here with us today. Roger, do you want to, what do you think is what the future holds, and what's going to drive the change that you see coming?
I think I'll make two comments. The one relates to VOCs, and I think you'll see in the coating space there's a lot of chemicals, harmful substances, and there's the two coatings that really make a lot of sense in this space are water-based products and 100% solvent, 100% volume solid solventless products, and that reduces the VOCs for both people in the environment that are working and the applicator. And the second comment is on durability, that we're looking for longer service lives, and people are expecting more and more of the intumescent, so a more durable intumescent for the future.
Thanks, Roger. And Jeff, your view?
Look, I'm just really grateful that passive fire protection and fire protection in general, there's a microscope over the industry now. I think it's about time that it was recognised as a proper trade nationally, like a plumber or a carpenter, because in the end it is about life safety, and I think it always gets swept under the rug, and it's like a second thought, oh my God, I've got to put a fire collar on, or I've got to protect a bit of steel, because it's a burden to a lot of people. So I really think it's good that it's really under the microscope and people are taking notice that it needs to be done properly.
And what a great way to finish up. And it certainly has been under the microscope, and it's great that there's going to be a lot of innovation that will come out of that. It is all we've got time for today, as always. And please, once again, join me in thanking Dr. Jonathan Barnett, Jeff Boone and Roger Tobler for their time and insights today. I'd also like to thank Engineers Australia's long-standing industry partner, Dulux Protective Coatings, for making it all possible. As always, we're looking for feedback, what we can improve on, what we can do better. And please, if you could complete a short feedback form in the description box below. On behalf of Engineers Australia and all of us, thank you again for joining us for this afternoon's webinar, and we look forward to seeing you again soon. Thank you.